Okay. So I think I'll start by telling people what phosphate is, because maybe you're not aware of it or how important it is. And the thing is, it's everywhere. And like, it's literally in our DNA. It's literally in our bones, and it's actually in everything. It's in our lipids, it's in our sugars, it's in everything that makes you up. I mean, take it for granted. If you get cremated, the pile of dust that's left over is calcium phosphate. So that's what's there. So it really is important for everything, okay? But the thing about it is, it's a finite resource. It's not like carbon that we've got endless amounts of sugar. We can constantly fix carbon, and all they need is sunlight and water to do it, and it's a renewable resource. Even nitrogen, which is an important fertiliser, bacteria fix it naturally. And there's other chemical processes, and there's lots of it in the atmosphere. But with phosphate, not so much. So it's in everything: plant, animal, bacteria, whatever. Now, ultimately, all our phosphate comes from stuff we eat. Okay, so whether we eat the plants or we eat the animals that eat the plants, it all comes from the phosphate, okay? And we'll have to try to go with this one here. So, but the problem is, in the soil, the phosphate is lost very fast. It's lost two ways. One is it's chemically fixed, so it's no longer bioavailable. Or it's washed out of it really, really fast into the water system. And I'll show you later on is that it's really funny, for a resource, only 10 to 30% of the phosphate we apply is ever used by plants. And if you think of any other process that you'd carry out, say a business would carry out, if it only used 10% of it, and the rest of the 90% was thrown away, you wouldn't think you'd pay hundreds of millions of dollars for it. But literally, that's what happens with phosphate. It costs hundreds of millions of dollars for phosphate fertiliser a year in Australia, and as little as 10 to 20% of it ends up in plants. So that's how inefficiently plants use it, and that's how costly it is for us. Okay, and it is kind of important, because it's not that it'll make things grow a little bit better. It really makes them grow a lot better. You would not have growth without phosphate. So it's not as if it'll give you the last 5 or 10% in yield or anything like that. It's absolutely necessary. It's a macronutrient. So it kind of like, so farmers, the cost for farmers, or arable farmers anyways, obviously seed is a cost, fuel is a cost, but fertiliser is the main cost. And that's phosphate, nitrogen, and a lot of phosphate. So we absolutely need it. So I think everybody in Australia thinks, oh, we easily grow enough food to feed ourselves, and we can't feed Asia. Unfortunately, we can feed at best 100 million people in the world. If agriculture was really efficient in Australia, we do 60 million at the moment. We might be able to double it and maybe quadruple it if things really, we got some real funding. But we can definitely never feed anywhere near the Asian population. But all the food we grow absolutely depends on applying this phosphate. And if we don't apply it in the morning, we wouldn't even have enough food to feed the population of Australia. Basically, to grow, plants need this much, 20 to 30 parts per million. But most land in Australia, and not only Australia, across the world, has much less in it. And that's because, as I said, phosphate very fast in soils either becomes fixed, and Australia has a particular problem with that because it's an old continent. So anything that was there is actually either washed away or is being fixed into inaccessible sources. Now, there is a few places in the world that still has some phosphate. For instance, there's areas in France and Belgium that would have a lot of phosphate, because all the explosives that were used in the First World War had lots of phosphates in them and things like that, and nitrates. So they're quite good places to grow. That's why all those fields look really nice with poppies in them, because it's actually very fertile ground. But I don't think it's a solution that we should actually use to actually so we need to come up with something better. But you can see that if you need 20 to 30 parts per million, which would be over on the really, really black dark side here, the heat map would be. But you can see in most areas we're really down to the 1 part, 2 parts per million in Australia, even in the productive wheat growing areas that we think are really quite high fertile and things like that. So it's not just marginal land that needs actually phosphate. That is, all agricultural systems have to actually get at it. Now, First of all, like everything, phosphate costs money. It's kind of a bit like oil and other commodities like that. The price does go up and down, although prices of fertilizers tend to stay reasonably high, because no matter what sort of global crisis you have, people tend to eat. You know, they might cut back on the extra bottle of wine every week or whatever, like, or not change the car every year, but they tend to eat. They don't skip out on a meal every day. Most people don't. And the price of food, this here is an index for production and fertilizer, and that's the other thing that's saying is that really to actually get increases in production, you have to put on more fertilizer. And it's a case of diminishing returns at the moment, that you've got to put on lots more fertilizer now just to get marginal increases in production. And we won't worry too much about all these figures over here, but this tells you the rate of phosphate and potassium that have to be applied in, well, the averages for the various states in Australia over time, and there comes like that. So you can see all the land is used in all the systems, and it's all actually got fertilizer added to it. And again, it's one of those things that is always a problem for producers, and it'll always be directly related in the cost of food. That the price of phosphate, just like the price of oil in Australia, we can't control it. Even though we have some phosphate in Australia, we're a net importer, but even though we have some here, we can't control it because it's the world demand that controls that. And the price of that will decide the price of food, which again, it's not such a bad thing in Australia. I mean, food goes up a little bit, it's not so bad. Because, you know, if you look at the amount of household income that's spent on food compared to a mortgage or a car or whatever, it's reasonably a low percent. But maybe for about 3 billion people in the world, the amount of household income that's spent on food is 80 to 90% of the income. So when food goes up 20 or 30% in price, they actually enter what they call the longer hunger period. There's always hunger periods in the subcontinent where people just don't have food to eat until the next crop comes in. And the higher the price of food, the longer that hunger period is. Like, so if the monsoon fails, or it's too wet, or it's too dry, or whatever, those periods are very. But also, the price of phosphate determines that. And in fact, just prior to the GFC, the Indian government, the Pakistan government, the Thai government were all preventing exports of rice. Purely because the price of food was going up, because the price of phosphate and fertilizers were going up. So you were actually getting a real issue with food availability. And some of the initial riots in the Arab Spring, as people would like to call it, started with the prices of food rising in those countries. So while they turned into political events, they actually started going back to the rise in price of food when governments started to remove subsidies from those things. So it's not only important for food, it can be important for the whole global political stability to keep these things relatively available and cost efficient to not only Australia, but to the world, because what happens elsewhere does affect us. So this just shows you that we do produce some phosphate, we do mine it, we have some big mining companies. If anyone reads the newspaper lately, they'll hear that some of our multi-millionaires or billionaires are in trouble with their phosphate mines, and they've been doing various things, but we won't go into that. But ultimately, we're a net consumer of phosphate, and it's required for food production in Australia, which is a big export commodity, okay? Agricultural exports is quite a large export commodity in this country. Okay, so what happens to it? So I've said only 5 to 30% of applied phosphate is taken up by the plant. So this is really quite a simple diagram. So, okay, you can go out, you dig it up somewhere. It doesn't have to be in Australia. Often in sub-Saharan Africa is one of the major sources it comes from now, or South America. It's applied, either the crops and then things like that. So then what happens is basically a lot of it runs off just into the water system. Because the good thing, for plants to take it up, it has to be soluble. When it's soluble, it tends to get washed away. Okay? The rest of it, some of it becomes chemically fixed in the soil, so it won't be available. And then it gets into the system. Now, there's two problems. There's a few problems there. First of all, that's not very efficient. Now, if you're throwing it, like, you know, if you went and you filled your car with fuel in the morning and you paid $50 for it, and then as you were going out of the garage, someone says, no, I'm taking back $35 of that fuel because that's all you're allowed to use, you wouldn't be very impressed. And that's generally what happens with phosphate. So that for every $100 of phosphate a farmer puts on the land, at best, they get the benefit for $30 of that. The second problem is that the $70 that's wasted goes on and causes other problems because it gets into the water system where lots of things like algae and weeds and other things like that kind of thing, great, will start growing. This is our fertiliser. So they actually use it to grow. So it's a major problem, say, in Queensland, just simple runoff, not only from agricultural production, because it's often kind of just saying, oh, the runoff from agriculture causes the problems. It's actually the runoff from our gardens that causes the problems. Okay, we all love pottering around on the weekend or not, or kind of putting in some plants, especially now we kind of think, oh, we'll do that and get some, let's go down to Bunnings or wherever and get some fertiliser and throw it on. Well, most of that will actually end up in the water system in 3 days' time. Cause algae blooms, cause weeds to grow, choke natural plants and animals that are in the system and kill them. And then there's a cost to that. There's an environmental cost, but there's actually a real cost as well because governments have to go out there and they have to find out what goes on and they have to employ people. So it actually turns out to be quite a costly process. And if you look at it with the Great Barrier Reef, well, apart from the fact it will destroy something that's actually quite unique, there's a cost in tourism. If the barrier reef isn't there, people won't pay to come and see it. So there's a cost there as well. So there can be lots of costs in that 70% that goes off that is not just directly got to do with the person who pays for it. Okay, so that's phosphate. It's, you know, you buy it in bags, superphosphate, blah, blah, blah. It's usually bought in mixes with various other things like nitrogen or potassium or whatever, things like that. Because if you want phosphate, you usually want the other macronutrients as well. But phosphate is a particular one. Now, because we had a, yep, it is a finite resource. So just like peak oil, there will be peak phosphate. We may be even there, we don't know. That's the problem. Okay? But there's no doubt about it, it's a finite resource. So the more and more we use of it, the more expensive it's going to get. And the more expensive it gets, the price of food goes up. And that will make it more expensive because people think, oh yes, it's worth getting into this business. So it is something that's going to run out. We're not sure. Some people say we should reach peak phosphate by 2050. Some people will say it's longer. It doesn't really matter because we do have to feed a lot of people. That's not an option we have. Like, you know, with peak oil, like, okay, we have to have energy for various things and there's various alternatives. There's no alternatives to phosphate. You know, you can't go with solar power, or you can't kind of decide to recharge the batteries or build nuclear or whatever other options you might think there is there. You can't do that, so you actually have to use it. And again, the IMF, is the International Monetary Fund Food Index, the price of food does tend to rise. It was rising really quite dramatically, as I say, pre-GFC. The GFC was actually a bad thing for developed countries. It was actually quite a good thing for some developing countries because it flattened the price of food in those countries. The fact that oil has gone down in price has meant that there's literally hundreds of millions of people in Asia that are not hungry because the other cost of food production is fuel. So once that goes down, the price of food goes down as well. And it's got nothing to do with biofuel that everyone thinks it's got to do with. It's got to do with food. You need fuel to transport food. You need it to farm, you need it to harvest, and you need it to transport, and you need it to manufacture. That's all energy demanding. So the cheaper the oil is, the cheaper the food is. They'll be always linked, and it's got nothing to do with biofuels. So these are various statements. I think everybody knows that we're going to need to feed lots more people in the next 10, 20, 30, 40 years. Importantly, the people, like by 2050, it's not as far away as it used to be. Like when people were saying this in kind of 1999, it's kind of, oh, it's a bit away, I won't really worry about that yet, but it's not that far away anymore. So if you think about it, is that people who are going to university now will need to solve that problem. So it's not a problem anymore that is for the next generation to solve. It's actually now for the generation now to solve it. So the people that are studying science, engineering, agriculture, water, social science, all those things there, they're going to need to solve that problem. Because those people are going to be there. Because it isn't that we're going to have 6 billion people now, and in 2050 we're going to have 9 billion. It's going to be increasing over time. So it's not just in 2050 all of a sudden the problem appears. That's the end point of the problem. And it's probably that's probably a very, what you'd call, conservative figure. Because there's very few countries when they undergo development where people's calories intake is what's recommended. So that's based on the daily recommended intake of calories. But we all know in developed societies like ours, we all consume too much, even though other people don't have enough. So the increase in 48% is really what we just need to actually be calorie sufficient, not for what society will demand, which is actually quite a big difference. So you need very large increases in production. You've got to remember that. You need that large increase. Okay, speed up. In production, we have less land. We'll always have less land. And we won't have more resources. So how do we do it? Well, the way we do it, we'll go through it, we do something like this. We use an iterative analysis, co-expression, enrichment, and protein interaction protocols. That's science for we guess. We do all that sort of stuff, which can take just person Josh Lynn 5 years to do. But by guessing and going through all that, we can have plants here that don't do so well. But we got plants here to do much better on phosphate, low phosphate, than the wild type relatives, the mutants that we make. And we've got these ones here to grow much better with phosphate and without it than the current ones. So we can actually easily find out the mechanism to make plants more efficient. And it's all got to do with, just like in real estate, location, location, location. You've actually got to have the right protein in the right place. It's got to be in the root. It's got to be in the right cell in the root. And it's got to be in the right location in the cell to do the job. And once you can figure that out, you can make the plants far more efficient. So for instance, with this one here, you can see this protein here. When you've got lots of phosphate, you can see the protein is present throughout the cell. But in phosphate limited conditions, you can see it's only in the plasma membrane. So the protein decides where to go in the cell based on the availability of phosphate. The other way we can solve it is nature already solves these things. Natural variation in nature means plants become very efficient to grow in low phosphate soils. These are from Western Australia, where it has some of the lowest phosphate soils in the world. But we can do it another way. We have a world phosphate map, but you can collect a weed that spreads throughout the world that we work with in the lab. Now, we don't call it a weed, we call it a model plant because, politicians wouldn't give you money to go around collecting weeds. But they grow on low phosphate, excess phosphate, and middle level. So if you look at those plants and set them up in the lab, you can see ones that are really tolerant to low phosphate. They grow normally, they don't care. And you can find ones that are really sensitive. So they've already solved it. So we know what the sequence of these plants are. It's reasonably easy to do. So we can plot them out to ones that are resistant, the ones that are sensitive, do some fancy genetics, and identify the genes that give the ones the ability to grow on low phosphate. We then just have to transfer that into crop plants. Okay? And this project here, we can even set up a system in plants that plants will turn on and off the lights when they're actually short of phosphate. So they will actually tell you, before you even notice as a farmer, that, hey, I'm hungry for phosphate, put some on. So that one of the ways you can save that phosphate being applied to the land is only apply it when the plant really wants it, and do it that way. So the take-home message is, phosphorus makes us happy, but we really need to use it a little bit more wisely. Okay, thank you for your time.
Thank in the water,
Yeah.
it doesn't go away, does it? Like, does it
It'll eventually
have
get.
to be there?
It'll be there. There is some levels of phosphate in the water, but the phosphate that gets washed into water will generally get either chemically fixed or taken up by some bacterium or algae or plant and kind of be used for. You can. You can actually. They're beginning to in Europe looking at taking phosphate out of runoff and reusing that in fertiliser systems. But you can imagine that becomes a costly process. But in an intensive European farming system where their environmental levels are now quite strict, they're beginning to actually have pilot plants to do this, to see how feasible it is in terms of energy and in terms of, yeah, like it's very hard to get all the water that runs off from agricultural land in Australia. But you can extract it from water to prevent pollution and to reuse it, yes.